Okay, fine. Okay, so next week I think you have your midsem exam, as far as I came to know. Um, so the syllabus for that next midsem will be from whatever has been covered in first midsem. After that, whatever is there till like maybe today. Okay. So after the first midsem, whatever is covered till today. Okay. Uh, কারুর একটা বোধহয় মিউট করতে হবে, হ্যাঁ, ওকে ফাইন। Okay, so so we were talking about classification problem, and um, just a moment, please. So we were talking about classification problem, and and this classification can be like supervised classification, and what is unsupervised classification, that is typically called clustering. So in supervised classification, last time what we saw was this Bayes classifier. In fact, what we saw is naive Bayes classifier. So what was our conclusion in the last class was that if you can have a Bayes classifier, then the error is minimum. The error of classification for a new data is minimum. But the thing is that in order to implement the Bayes classifier, you do not have enough information from the data, and it's not possible actually that way to compute the interactions of different events or different attributes. So that is why simplification of that is kind of naive Bayes classifier, where we assume that all these attributes or events in terms of probability are independent of each other, and in that fashion, and if you assume that, then we can use our Bayes theorem in order to um, find a class for a new input data. Okay, so this is one method we have seen. The second method that we have seen is that KNN method, right? We also saw in KNN method how do you find this K, find this K using this elbow method. Okay. So in KNN method, simply what it does is, so it is a non-parametric approach, if you remember. So in this method, what is the main thing that given all the data set, you actually classify a new data point with the concept of this nearest neighborhood. So whatever is the points that are near to this new point, we simply look at its class, and whatever is the majority class, we assign that class to this new data point. Okay. So then here the factor is how you choose k. So we saw that choosing a very small k value or choosing a very big k value, both are a bit of problematic. They create the problem of overfitting or underfitting, and that's why a balance k that you need to find out, which is typically between 5 to 10. That's what people have observed. So if you find a proper k, then it gives a good results for data sets which are basically non-linear. So it performs good for non-linear data. So then, so although we have not still talked about the metric for saying that it is metric for performance. So actually, you know those metric for performance, but okay, maybe at the end we will talk about it. So it is basically those confusion metrics that we are talking about. Okay. So in both cases, these are all, since it is supervised classification, so these are all labeled data, right? So the third algorithm today we will be talking about, again for classification problem, is what is called the support vector machine, or in short SVM. Okay. So like other supervised classification methods such as naive Bayes or KNN classifier, what you are given, is the vector xi. So I'm writing it like this. So these are the attributes, and yi is your label. Right. So xi is the data vector, okay, and yi is the label. So I haven't put a vector on yi because it is a single element. Okay. So now this particular problem, it means that, so what we want to do is that we want to build a model, Oh, by the way, I don't have the slide for this. So as I write, you can take down these notes. Okay. Or maybe I will save it and send you, but still I will say that you write it down even in your notebooks. Okay. So I don't have the slide prepared yet. I will try to prepare the slide, but I am not very sure whether I'll be able to complete it. So it's better that you take notes of this, and I will also try to give this as a PDF form. So we want to build a model such that for a new point, for a new data vector, or you can think of it as a point. Okay. Pi, that's why I'm calling it to be Pi and putting this vector mark over here. We can predict its class. We can predict its class. So that's a typical supervised classification problem. So now this support vector machine, it can be formulated as a linear problem, or it could be a non-linear problem. So what is the meaning of the problem being linear and non-linear? So that you have already seen for classification problem. So, and also of course this SVM problem can be defined for binary classification or multi-class classification. So what is the meaning of linear and non-linear? So suppose you have different data points. Let's say this red dots and maybe some blue dots. Okay. So when we say it is a linear one, that means we are able to kind of the data this, so there are two, so I'm talking about a binary class. Okay, binary class with x1 and x2 values. So if you plot it like this, I hope you can see this. I think it's too small. So these are the data points I'm talking about. Should have drawn it little bigger. And these are the data points. So when we are talking about linear SVM, then there are two classes, red and the blue. So what I'm talking about is that it is possible. So this data set is separable. So it is possible to draw a line uh, to separate the data sets into two classes in when it is a binary classification problem. Okay. So obviously, if you have a non-linear kind of thing, then definitely the boundary is, I mean, it's no more a line, but a non-linear structure. So, for example, it could be something like, and suppose you have this kind of things. So you see that there is no separate, I mean, there is no line which can separate these two classes. So in that case, possibly the separating line will be something which is non-linear. So it is something like this. Okay. So for the time being, we are only going to consider the mathematical formulation of this linear classification. Okay. So linear SVM, linear support vector machine. Okay. So if you know the history of this SVM, actually it started around 1970. That's something very surprising that it started around 1970. Okay. So what that time they tried to do is uh, that the machine should learn the mapping from xi to yi. So the machine, how can the machine learn? So it is much before when really AI and all those things came up. So how the machine learns the mapping of this xi vector to yi. Essentially, this is what is actually the classification problem. So given a data set from here, write a function that will map xi to yi. Right. Okay. So now how this formulation, how the problem is formulated. So let's first write down some of these notations that we'll be using in order to do the formulation, problem formulation. By the way, let me know if there is some, if you have any questions or anything, because I'm not able to see anyone's face. Just a minute. Okay. So what we consider is that each observation, or what you say, the data observation consists of a pair this xi. So this I have written earlier also, xi yi. Okay, where this xi is a vector which belongs to the space of r to the power d. So that means it is a d-dimensional vector. Okay, and this I, so these are the observations. I corresponds to each observation. So I equal to, let's say, 1 to some L observations are there. And okay, by the way, we are talking about binary classification problem. Binary classification using SVM. This is what we are going to formulate. And the associated label. So this associated label, we are making it in this fashion. Associated label yi equal to either it is a +1, +1, or it is a -1. So there is a reason for making it in this fashion for this binary classification, +1 and -1. It will help us to formulate the problem. Okay. Okay. So there are two classes. So maybe the truth you represent as +1 and the false you represent as the -1, something like that. Okay. Then insert the page. Okay. So that means this yi belongs to either +1 or -1, and xi belongs to this space of d-dimensional vector, xi vector. Now what we are trying to do is that since this is a linear separation as we have seen in that figure, so we are able to draw a clearly we are able to draw a line which clearly distinguishes the two different classes. Okay. So now this line, we can say it is a line when when the data set is in 2 dimension. But when the data set is in d dimension, then we have to think about a hyperplane. Okay. So a d-dimensional hyperplane, we have to find out which separates these two different classes. Okay, but for visualization purposes, I'll be drawing those graph. So for visualization purposes, we will stick ourselves into 2 dimensional data, but it is extendable to any d-dimensional data, and that's why instead of saying it is a line, when we are really develop this theory, we will talk about a hyperplane. So suppose we have a hyperplane. We have a hyperplane that separates the positive classes from the negative classes. Okay, so what that means that there exists a separating hyperplane. If there exists a separating hyperplane, then support vector machine will find exactly that hyperplane. Okay, so that is the strength of this support vector machine. So if you already know that your data set is more or less very far apart, so that time you can use this support vector machine because we are going to get the optimized result for any prediction. That is the strength of this support vector machine. So what this algorithm actually looks for is that, so for the linearly separable case, so this is what is very important, this linearly separable. For the linearly separable case, the SVM algorithm actually it looks for a separating hyperplane with what we call a maximum margin. Okay, so this is what is important. So it looks for a separating hyperplane with a maximum margin. So from this statement, probably you can see that we are going to formulate a maximization problem, similar to how we have done for PCA. Okay, or another thing we did, right? Which one we did? I forgot. Another one we have done, linear regression, right? So for everything we have done either a maximization or a minimization problem. Okay. So now what is the meaning of this largest margin or maximum margin? Okay. So maximum margin or the largest margin. So now let's visualize it in the 2-dimension. So 2-dimensional data, we have this, let's say x1 and x2. So the data is like x1, x2 and that y. Okay. So this is the data. That's what you have. So this y is going to be either +1 or -1, and this data is a 2-dimensional point. So if that's the case, let's say I'm taking a typical example to show you what is this. Let's say I'm taking a red class. So the red, let's say there are just 4 points. Another, let's say blue, and these are over here. Okay. So these are the points, one plus positive class and the negative class. So now the meaning of, so this side is positive class and this side is minimum class. So what is the meaning of this maximum margin? So the meaning of this maximum margin is, let's say I am able to draw a line. So sorry, it's not becoming a line. Just a minute. Let me see if I can draw some line over here. So now I'm not able to see. Just 1 second. Let me see if I can draw a line.
ম্যাম ওই স্কেলটার পাশে আছে মনে হচ্ছে।
কোথায় বলো তো?
স্কেলের মতো একটা আছে আইকন, ওর পাশে।
সত্তরিয়া। এইটা বলছো?
হ্যাঁ।
কিন্তু স্কোয়ার রেক্ট্যাঙ্গেল কিছু হয়ে যাবে মনে হচ্ছে। আচ্ছা দেখুন, দেখা যাক। না, হচ্ছে না এটা। ওকে, যাই হোক আমি কোনো রকম একটা আঁকতে পেরেছি। Okay, so this is the line and another line, let's say. So which is actually, see what I'm trying to do is now it has come a straight line. Fine. So this red point, after this red point there is no other point towards this blue actually. So that way I have drawn this line. And beyond this minus there is no other minus in this. So basically I am talking about this. This is the margin that I am talking about. So this is the maximum margin. This is that maximum margin I am trying to find. Okay. So what is this maximum margin? Which separates the two classes such that the distance between these two classes is maximum. Okay. So in order to do that, actually, we also define actually not define, we define a median line over here. So this is the median line in this region. Okay. So what we call is that this one is the positive decision boundary. Okay, and this one is called the negative decision boundary. How we find it, we will come to that. Okay. So now for a new data set, okay, anything in this region will be treated as belonging to the negative class, and any point in this region will be treated as a positive class. Okay, in this region and beyond. So this is what we are actually trying to do. Okay. So let's call this part to be D plus. I mean, this portion from the median line to the positive decision boundary. Let's call this to be the distance to be D plus. Similarly, this point, I mean this distance, so let's call it to be D minus. Okay. So now let's talk about this margin. So what is this margin? So let this D plus or D minus be the shortest distance from the separating hyperplane. So in our case, this separating hyperplane is nothing but this median line. Okay. To the closest positive, I mean in case of D plus it is positive, for D minus it is negative sample. So that's what, right? How I have drawn these two lines, this positive decision boundary and the negative decision boundary, which actually, even though I have not drawn properly, so which actually touches the closest, so it is basically the distance from the separating hyperplane to the closest positive or negative sample. Okay, so this one, B plus. Similarly on the negative side also. So now what is our objective now? So our objective is, now it suddenly became round. Okay, let me read. So our objective is to find the maximum margin or the largest margin. And so this is one of the objective. And after that, how do we use it for our prediction? So we want to make a decision rule. So to make a decision rule, that would use the decision boundaries. For prediction. Given a new data point. So now how do you formulate this? So let's draw this diagram once again. So let's say this, now it is coming out to be straight. Yes. So we'll talk about again those red thing, and maybe over here, and those negative ones, blue. Negative classes are, I'm considering it to be blue, and this. Okay. So this is the negative class, let's say. So as before, let's draw the margin. So this is the, sometimes it is not doing it straight. Let me see. Okay. So I mean, take it in this way that these minuses are on this line, okay, because that is deciding the boundary. Okay. And this red one is actually should go through this. No, it's not doing it. It's not making it a straight line.
ম্যাম এই লাইনটা কি লিনিয়ার রিগ্রেশন করে করতে হবে নাকি নর্মালি কি করে হবে?
হ্যাঁ, কি বুঝতে পারলাম না।
লাইনটা যে ড্র হচ্ছে সেটা মানে ম্যাথমেটিক্যালি লিনিয়ার রিগ্রেশন
আমি আসছি, হ্যাঁ, উইল কাম টু দ্যাট। সেটা যাতে আগে ভিজুয়ালাইজ করলে, ইফ ইউ ভিজুয়ালাইজ বিফোর, দেন ইট ইজ, I mean, you'll be able to find how you are getting this line. Coming to it.
ওকে
Okay. And let's say the median line is this one. Let's take a different color. And so median is more or less like this. Okay. I haven't drawn very well, but okay. So the margin is now, so let me just write down. So this is the median, this is that positive boundary, and this is the blue one is the negative decision boundary. Okay. And margin is defined to be this one. So this one is the margin, right? From the red line to the blue line. Okay. So now let's name these points. So let me say this is P1, this is P2, this one is, let's say, P3, and this is P4. Okay. So you see that this point P1, okay, I'm just, it's actually a point I'm talking about, right? So this point P1, it is on this boundary, okay? And this is also on this boundary. P3 is this point on this, and this is P4. So this P1 is actually a vector. Okay. So I'm calling it to be a vector U. Okay. And then I am drawing a line. Okay, let's take another color. I'm drawing a line which is perpendicular to this median line. Okay, let me just draw that also. So it is perpendicular to this median line. So this thing is called, let's say, W. So it is a vector. Okay. So now I am drawing a projection of U on W. Okay. So this is also in pink I am drawing. So U is a projection of U on W. Okay. And this projection, meaning this part of it, okay, I'm naming it to be C. projection is basically a length, right? So this length I am calling it to be C. Okay, so note that this distance is actually going to say something about where this point P1 lies or with respect to this median line. With respect to this, not exactly the median line, but with respect to this vector W, which is perpendicular to the median line. Okay, so now with all these vectors, we'll be able to define this margin. How? Let's see. So what we have done, let's write it down. So let's go back to black color. Yes. So let U be an unknown point. So we are doing it in terms of any point because ultimately we will be predicting for a new point. So let's say that U is an unknown vector. Okay, unknown vector for which we want to decide the class. So basically what we want is, okay, so we want to know where in the where U lies with respect to the median line. Okay, where U lies with respect to the median line. Whether it is above the median line or it is below the median line. If it is above the median line, we can say the class of that is positive. If U lies below the median line, then we can say it is a negative class. Okay. So these zones are, so actually we can say whether it is within the margin zone or beyond that. Okay. So we can, like, first thing we can see whether it is in the margin zone. These are the possible zones, right? Left of the margin, and third, the right of the margin. So the left of the margin is basically your negative class and right of the margin is your positive class. So that is how I have defined my left and right. Okay. Now, so in order to know this where U lies with respect to this median line in the margin zone, left of the margin or right of the margin. So to know this, what we do is we project this U. It's exactly what I have said right now. You project U on W, which is a vector perpendicular to the median line. Okay. And so we project U on W, and what we see is that, and so and see how how large or how big is the quantity to infer where U lies. So what is this meaning? See, if you look at this figure, I said this distance to be C. So I want to see how big is this C. So that I can, so this C could be either in the left part of it, within the margin zone, or it may be beyond this red line, to the right of this red line, right? So that is why I compute the projection of any point on this perpendicular line, perpendicular to the median line. So how big is this C? The projection of U unknown vector onto this normal vector. So depending on this value of C, I can decide whether it is to the left of this blue boundary, within the region, within the margin from blue boundary to the red boundary, or it is beyond the red boundary. Okay. So now what I have written right now, that we project U on W and see how big is the quantity to infer where U lies. Okay. So we know from our linear algebra basics that this projection C, how you can write it? You can write it as W is a vector and U is a vector. So essentially it means that WU is greater than equal to C. Okay. So now, so that is W dot, what I have said over here, it means that essentially we are formulating as W dot, the dot product of W and U, which is nothing but this projection, is greater than equal to C. Now, what is this value of C? So this is the kind of rules we were talking about, okay, to decide which class it belongs to, right? So if C crosses the median line, then data point is positive, else it is negative. Okay. So this is the simple basic geometry that we will use to formulate the support vector machine. Okay. So what we are doing then, just to summarize, we have any unknown point that is a vector. We project that on a line. So we project that on a vector that is perpendicular to the median line of the maximum separation between the two different classes. And the assumption is what? Assumption is that there exists a separable hyperplane between the two classes. Okay. So now let's go step by step for the formulations of the problem. So what is the step one then? We formulate the decision rule. Formulate the decision rule. The decision rule is nothing but what we have just said over here. Okay. So we'll write it algebraically. So what we will say is that, so we say that this W, this dot product of W dot U dot, which is that vector projection value, plus some B. Just 1 second. Last minute. Yes. So we formulate this decision rule. So we say that this dot product W dot u plus b is greater than equal to 0. Okay, so instead of writing this, so this, what is this plus b? There will be some, because we are saying that if it is, if that c value crosses the median line, then the data point is positive, else it is negative. So this b actually, or the value of this b actually decide how much it is, I mean, how much how much to be added with this so that it crosses that median line. Okay, so that way you can think of it. So how much to be added to this so that it becomes a, or other, in other words, we can say that how much amount, so this b you add to this so that it becomes a positive sample. So we say this w dot u plus b is greater than 0, then it is a positive sample. It's a positive class. Okay. So let's call this equation to be 1. We'll be coming back to this equations once again. Okay. So, or maybe, okay, let's write that b. What is that b over there itself? Okay. So just to write once again, emphasize where u, sorry, w, you already you know, w and b are unknown parameters. Unknown, we have to find them. We have to find them. Right. B is that value when I will say that it is in the positive class, and W is that vector that also we need to find out. So that's why W and B are unknown values that we need to find out from the formulation. Okay, but once we find this W and B, then what you will do, given a new point, you simply use this equation to find whether it belongs to the positive class or it is a negative class. So that's why we are calling it to be a decision rule. Okay? Okay. We have to find them by formulating a optimization problem. By formulating an optimization problem. Okay. So next, let's see. So for any new data point in the margin zone, the decision rule says, that if this w dot u plus b is greater than 0, then it lies to the right of the line L, right of median line L. I'm calling it this median line to be L so that each time I don't have to write median line. Else, if this dot product u plus b is less than equal to 0, that means then u lies to the left of line L. Okay. So basically what we want is, we want a maximum margin. or large separation, that way you can say, large separation between positive and negative samples. So from here what we can write is as follows. So for positive samples, samples means sample data, I'm saying, for positive samples, so that we are denoting it like this. Okay. Positive samples means the data set for which the label is positive or +1. What we do is we insist that this W U plus B must be greater than equal to 1. Why we made it, instead of that greater than equal to 0, we made it 1? Because we want a large margin. Okay. So this we are calling it to be equation 2. Now similarly, we can say for negative samples, X minus, we insist that this W U plus B, it must be less than equal to 1. Okay. How it comes out to be? Since, okay, so this we want like this, that W U plus B must be less than equal to 1. So then it is going to create a margin. For what values of W and B, we are going to get these two equations satisfied. Okay. So now the point is that we want to now merge. See, for positive sample and negative sample, there are two different equations. So it is kind of difficult to formulate the problem. So that's why we want to merge these 2 and 3, these two equations into one simple form, so that it can be used for this optimization problem formulation. So for that is very simple. So we multiply yi on both sides of 2 and 3. Okay, so as a result, what happens? Since yi is nothing but +1 and -1, remember that yi is nothing but +1 or -1. So if you multiply yi on both sides of 2 and 3, then what you get is, one you get is yi into wi xi plus b. So I'm writing instead of u now this xi. Okay, xi plus, right? So this is plus also. Xi, so this is a plus b is greater than equal to 1. Okay. Since yi is equal to 1, okay, and then we can write, so let's call this to be 4, equation 4, and similarly yi into wi xi, so it could be plus or minus, whatever it is, plus b is, so when you multiply this term, this 3 with -1, then what it becomes, because yi value is -1, right? So that time we can write it as, so this corresponds to 2 and this corresponds to 3. Okay, so then we can write it as well, this one also as 1, because this entire thing is getting multiplied by a -1. Okay, So that's why this equation now becomes yi into wi xi plus b is greater than equal to 1. Okay, since yi is equal to -1 for negative class. Okay. So you see now we have got a general formula for this. So let's, if I call this to be 4 and this to be 5, so we see that this 4 and 5 are same, right? Okay. Now once we have this, so what we will do is we will rewrite this 4 and 5 as yi into wi xi plus b. So this 1 I am taking to the left hand side and it is greater than equal to 0. And let's call this to be equation number 6. Okay. So now let's go to step 2. Now step 2 is that, see, there is a greater than equal to kind of thing. What happens if it is equal to 0? Equal to 0 means it is on the line. Okay. So let's talk about what happens if it is wi xi plus b minus 1 is equal to 0. So let's say this is equation 7. So what it means, you know, if it is equal to 0, that means these points are on the decision boundaries. Because since why we are talking about decision because boundaries, because I have taken this -1. Remember this figure. Remember this figure. So I did not make it to be, I want to maximize this zone. So that's why we have set, you see over here, this w into u, w dot u plus b is greater than equal to 1. So that I get a margin of that 1. Okay. So that it is not on that line. Okay. So when it is equal to 0, that means, what does it mean? It means that the point, this point is on the decision boundary. So if you look at this figure that we have drawn earlier over here, so you will see that these points P1, P2, P3, they are all on the decision boundaries. So for these 3 points, that equation will get satisfied. But for this point P4, the equation will not get satisfied. Okay. So maybe for understanding, we can write it down as that. So see that samples P1, P2, P3 satisfies equation 7, but not P4. Okay. So now our objective is to find out how to arrange for a line such that this margin zone separating the positive samples and negative sample is as wide as possible. So that maximum margin. So far what we could do, we could express the margins using this equation. So actually this equation expresses the decision boundary. Okay. So now we have to express it in such a way so that it maximizes the that gap, so that margin. It maximizes the margin. So now the objective is to find out how to arrange for a line such that the margin zone separating positive and negative class is as wide as possible. So that means what? After writing this decision, the lines representing the decision boundary, I need to represent the margin. Represent the width of the margin. Using again some vectors. So how can you do that? Again, let's draw the figure. So I will draw the figure a little in short. So here were our minuses, here was our plus. Okay, so we need to draw the line. Okay, the blue line is over here, the red line is over here. The red line is over here. Okay. The drawing is not good. Okay, forget it. Okay. So let's take this black here. Okay. So let's choose one x minus. I mean, this is a sample x minus. So this point, okay. And let us choose this as x plus, which belongs to two different classes. So I want to define this gap, right? Define this width using these vectors. So for that, what we do is, so these are actually the vectors. So this is x minus vector, and this is x plus vector. Now you can see very nicely this gap can be calculated like this vector. What is this vector? So this vector is nothing but x plus vector, I mean x plus minus x minus, right? Are you getting it? So this vector. So I am interested in this vector, which is the distance between 2 points which defines the boundary, one on the negative side, one on the positive side. Okay, so that means what I am getting is this vector. So width of the margin zone is defined as this vector x plus minus x minus, right? Which is actually a difference vector, right? So this way I can define the width with this vector. So once you have defined the width of the margin, so now we need to think about, we were talking about that you need that vector W, right? So if we have a unit normal vector W, you remember, from which I was computing the projection of any point onto the normal vector perpendicular to the median line. So we have a unit normal vector W to the line. You remember this L means the median line. Okay. Then the dot product of W with difference vector will give me the width of the region. So here this is a vector, right? This width of the margin zone that I am trying to define. So when it is x plus minus x minus, so this is a vector. But what I need to find is these vectors, again this vector's projection on the unit normal vector, this W, on the median line. So we can say, so width is actually a what scalar parameter, right? Here what we define the margin, when we define this is the margin vector, right? So the width now will really become okay. So this width then now becomes this dot product of the difference vector with the unit normal vector. So it is x plus minus x minus dot. So if this is not a unit vector, we make it to be a unit vector, right? So this means the magnitude of the vector W, right? So this becomes our equation 8. Okay, so dot product of the difference vector with the normal vector. Okay, let me add a page. So as I said, this is a vector perpendicular to median line L. So this will become a unit normal vector. Okay. Okay. So what we do is we evaluate this step for the points, this whatever belongs to the class of x, for all the points belonging to x plus plus and to the x minus class. Okay. So these are, so remember that this x plus and this x minus are points on the decision boundary. Okay. So what do we get? So for x plus, since yi equal to 1, okay, so that that step 2 where we had the equation that w dot x plus b equal to 1 will become w x equal to 1 minus b. Okay. So did you understand this step? So we have taken yi into wx plus b equal to 1, right? So there when you substitute this yi equal to 1, so earlier there was a yi over here, right? Instead of this yi, 1 gets substituted, and as a result what you get is this wx plus b equal to 1. So wx plus is 1 minus b. Similarly for x, what is some classmates? For this yi equal to minus 1, and so for this step 2 will become w this equal to minus 1 minus b, right? Because now yi is minus 1, so minus 1 multiplied with this particular thing, so then it becomes w. I mean, if you do the interchanging of things, then it becomes, I mean, take the things algebraic manipulation, you will, if you do, you will get it w x minus equal to minus 1 minus b. So let's call this equation to be 9 and this equation to be 10. Okay. So now we will substitute these values in that width equation. So substitute this 9 and 10 in equation 8. So equation 8, if you just, let's go back to equation 8. Equation 8 is the expression for width. Okay. So it's the equation for width. So it becomes what? W dot x plus minus W dot x minus into 1 upon this. So you have understood, right? W I have taken it with inside. Okay, just see over here. So this W I have taken along with x plus, and this W I have taken with this x minus. Okay. So that's why it has become like this, and into 1 divided by this magnitude of W. Now this is nothing but, now we have seen just now this W, yes, so W x plus is nothing but 1 minus B. So you just substitute there 1 minus B minus 1 minus B, right, into 1 divided by this W. Okay. So what it means is, it is nothing but 2 divided by, so it gets cancelled. You see, plus B minus B plus 1 minus B, and this 1 and 1 comes out to be 2. So it becomes 2 divided by this. Yes. So what do you see? Let's call it equation number 11 now. So this is the expression of width, don't forget. Okay. So now, so the point is that initially we had 2 unknown values, B and W, right? So from there I have come to an expression like this, to this W. So now what we want to do is, we want to maximize this width. So maximize width means maximize 2 divided by this. Now essentially this 2 is just a constant, right? So you can also say that it is maximization of 1 by this, right? Or even you can say, so keeping it in the denominator is very difficult actually. So what we can say is that instead of saying maximizing this, we can also say minimize this, right? So ultimately then this becomes our objective function. So our objective function becomes, for the optimization problem, for optimization problem becomes minimize this, okay, subject to certain constraint. What are the constraint? Subject to constraints. What constraints? That yi into w xi plus b minus 1 is equal to 0 for every I. Where from this constraint is coming, you remember? This is defining, this is the definition of the margin. You see, I want to, so I want to find the boundaries based on those xi which are at the maximum distance. Xi that belong to two different class and which are at the maximum distance. Now these, so the boundaries are going to be defined by one of the points in the data set. So that is why you are having this xi. And you remember that plus b, it is the distance of this point from the, I mean this plus b is like, I mean which is going beyond that decision boundary, right? So the objective function then now becomes this: minimize the magnitude of the unit normal vector subject to the constraint that yi w xi plus b minus 1 equal to 0 for every I. So for every data point, you'll be having its corresponding equations like this, a set of equations. Okay. So now you see this, you have also seen earlier that whenever we have an objective function and it is like there is a subject to constraint kind of thing. So then we have to apply a Lagrangian multiplier so that the constant can be added to the objective function of this minimize w. Okay. So now let's do that step then. So this optimization problem is a what is called, okay, there is another step. So one more step. So this minimize w, okay, for derivative computation, we are doing some kind of algebraic manipulation to it. So we are writing this w in the form like this: half of this square. Okay, so this is an important step actually. I have written it very, let me write it properly. So since it is a minimization problem, somewhere we'll be doing it, equating it to 0 and finding the derivative. So that is why, okay, let me write it more clearly. So for simplification, for simplified derivative computation, computation, rewrite above as minimize half of W square. Okay. And to add the constraints, we'll see how this form becomes useful. We write it so that when you find derivatives, then your constant just gets cancelled out. We'll see how it is helpful. To add the constraints to the objective function, use again this Lagrangian multiplier. And so as a result, what we get is let's say we are having a new variable minimize L, where L equal to half of this W square minus, when you apply a Lagrangian multiplier, note that here it is written for every I. Okay, so for each I we will have a separate Lagrangian multiplier. So minus, that's why we have a summation of over all your data points I, one Lagrangian multiplier for every entry, into yi into w xi plus b minus 1. Okay. So this entire thing. Summation is applied over this entire thing. Okay, so this is, let's say it is, okay, I have skipped some numbering. Let's say this is 2. So this is 12. This 12. Equation number 2. So now this equation is 30. So here alpha is the Lagrangian multiplier. Okay. So now since it is a minimization function, again we'll be finding out those derivative and all those things. Okay. Okay, just 1 second. Just. Hello. Hello. Are you there?
Yes, ma'am.
Yes, ma'am.
Okay. So, yes, 1 second. Okay. So, what we will do in order to do this maximization function, we need to find the derivative. So, find the derivative. Okay, let's go to the next page. Yes. So we do it with respect to this unit vector. Okay. So this is equal to, now you will see what is the advantage of having it. So when you take the derivative of this w with respect to w, then what, this 2 comes out. So this 2 and this 2 gets cancelled out, right? So that is the reason we have formulated it as half w square. So when you take the derivative, it gets cancelled out, and it's easy to do the algebra for it. So it becomes half into 2, this thing, and this cancels out. So that's why it is taken in this fashion. So then it is going to be minus the summation of, so this summation is always over this I. I'm not writing it anymore. Alpha I yi xi equal to 0. Now from this, what you get is this unit normal vector is equal to, this unit normal vector equal to sum over alpha I yi xi. Right? Now you notice one thing. So let's call this to be 14. So you have obtained the value of this normal vector. So what do you see? You see that this is a linear sum of some samples for which alpha I is not equal to 0. Can you relate with something? See, yi xi. So this is, I mean, it means this summation alpha I yi xi. So this W becomes a linear combination of some samples for which alpha is not equal to 0. So this means what? It is a linear combination, right? So it is linearly independent. Okay. So this way you obtain what is the value of W. See, all these values are known, yi and xi. And these are like taken, considered already, right? So next what we need to find is that B. You have a B over here, right? This also you need to find out. So B is basically that distance from the point, given point, which will help you to tell whether it is which side of this line, right? So we need to find B. So now next you find B. So for that what you do is del L del B. So if you apply this derivative, okay, by the way, okay, I've given a number to it, okay, yes. So if you do this del L del B, you see, look at this part of it. So that means it will be alpha I and yi, that's it. Rest of the things will become, when you take the derivative, it becomes 0. Right? So that means it becomes summation over I, alpha I, yi, and we have to equate it to 0 to get the values of B. So now we will substitute this equation, the equation for W, 14 in equation 13. So what is equation 13? Let's go back. It's that maximize that entire objective function. Okay. So we are substituting the value of W into the objective function L. So what you get is L equal to half of, put the value of W here, right? So W value is what? W alpha I yi xi vector. So I'm writing it twice because it was square. The summation alpha j, okay, yj xj, okay, because it was a square term, okay. Then minus, it was alpha I yi xi into summation of, I'm just substituting, okay? This minus, so you have to see that and see if all the corresponding substitution is correct. Yid plus summation alpha I. I'm doing substitution and doing the algebraic manipulation. So now this you can write it as again half uh, the summation alpha I yi xi, then summation alpha j yj xj, okay. Let me write it properly. Xj, okay, minus the rest of this part, this alpha I yi xi into this summation alpha j yj x. Now you see one thing, minus this thing alpha I yib. Okay, so this part alpha I yib, this part becomes a 0. Why? Because you see here alpha I yi is 0. So this part becomes 0. Okay. So this you get it from 15. Okay. So this part becomes 0. So this minus, this thing will not be there. So only simply will be having a plus summation alpha I. Now if you again do, so then L becomes summation alpha I minus half. Since it is, these two summations are there, summation over I and j, alpha I, alpha j, yj, xi, xj. So I'm rewriting in this fashion. So what we found from here is that optimizing L we see that L depends on the dot product of sample data. Right? So here it is, you see the dot product of this sample data over here. Okay. So now once you get this optimized line or optimized what width, so this L correspond to actually that optimized width. So once you have this optimized width, in order to predict the class for a new data set, we need to use the decision rule, right? So by optimizing, we got W, W and B. Then we take the decision rule of step 2. I think step 1 it is. Yes, in step 1 we define the decision rule. Let me write it properly. Step 1. Step 1, to identify a class for a new data point as follows. So W we have found out, right? W value is nothing but this summation alpha I yi xi, right? So summation alpha I yi xi. So this is that W corresponds to that Wi dot. It was that data point, right? Xi. So this Xi is this new unknown point U. Okay. Plus B. B value also we have got. What is the B value? B value also we have got where? Yes, from here. So we have also got this B greater than equal to 0. This implies, if this is true, if true, it implies a positive class, else a negative class. Else, if this summation this yi into xi dot this plus b is less than equal to 0, then this implies it is a negative class. Okay. So did you get the point how it is, how this, so maybe in support vector machine that you have studied earlier, you have actually used this formulation. Okay. If you just try remembering what formulation you have used in order to calculate a class for a new thing. Probably you did not know how it is derived, why it is in this fashion, right? So this is the point, how given a new point, why the formula is like that. So given a new point, you simply use this formulation. So where these are all actually the data set, this yi, xi, all these are from the data set. Alpha I is a like given parameters which actually decide the, which is basically this Lagrangian multiplier, right? So you obtain U and B values from the given data set, and then for a new data point you simply apply this formulation and say whether it is a positive class or it is a negative class. Okay. So this is about this SVM. Obviously, like this margin that we are talking about, this margin is a kind of what we call a hard margin. Okay, so which clearly describe the decision boundaries. Decision boundary. Okay, but it is also possible to have some kind of possible to have some kind of soft margin, so which we have not discussed here, where actually what you do is you allow some kind of relaxation, apply some kind of relaxation. So the meaning that the margin boundary, the decision boundaries are not precise. Okay. And obviously, so when you should use of SVM, obviously when you have high dimensional data set, so it is effective for high dimensional data. But of course, you some kind of dimensionality reduction technique may help to get, so some dimensionality reduction technique, helps better result, helps in getting the better result. Okay, so this is about the SVM. So anyone has anything to say? Have
One
you got
question.
there? Yes.
Ma'am, in these two equations, the inequality is not strict on both the sides. So if
Yes.
something is say equal to 0 or something falls exactly on the median
Yeah.
line, then
Yes.
how do
That
we?
means yes.
Yes, ma'am.
That means you can treat them either as a positive class or a negative class.
Acha.
So that time, that soft I mean, giving a soft kind of boundary will possibly help, or maybe yes, there is that problem of like, I mean, if it becomes equal to 0, then uh, it could be either this positive class or a negative class. That problem is always there.
Okay, so we can define
Uh,
either of those two.
yes, yes.
Okay, ma'am.
Just 1 second. Mm, I'll check it once again. Yeah, it could. You can treat them as if as a positive class or a negative class. Boundaries are always a problem actually in any kind of classification problems where their boundaries are very hard.
Hmm.
So this is where is a hard boundary becomes a problematic thing. So actually that means the class boundaries are not very wide if it happens like this. Class boundaries are very, that gap, the width is very small maybe. In that case, that might happen. Okay. Anything else?
No, ma'am.
Hmm. Okay. So that Shubhra, you give me this attendance. Okay. Send me the attendance. Okay. Shubhra is there or gone? Hello. হ্যালো যাবো কেউ কথাই বলছে না
হ্যাঁ ম্যাম, ওকে বলে দেবো ওটা দিয়ে দিতে।
হ্যাঁ ঘুমিয়ে পড়েছিল যাকে তো so give me the attendance okay
ঠিক আছে ম্যাডাম, আগের দিনগুলো আছে, ওটা একবারে অফলাইন ক্লাস হলে আমি দিয়ে দেবো।
হ্যাঁ, তাহলে দুটো একসাথেই দিয়ে দিও তাহলে একবার।
ঠিক আছে।
ওকে, ঠিক আছে, তাহলে আমি বেরিয়ে যাচ্ছি তাহলে।
Thank you.
হুম।